I put it on the calendar.
I don't think anybody looks at that.
Oh, they should announce it here.
I guess
It's not a floor plan.
I guess 8 people will know, but
Well, and Joseph and Sarah.
do they?
Yeah, because I told you guys it was on.
I knew, so I guess they know.
Yeah.
Yeah. I hope they haven't forgotten. And is the speaker here? Or?
No, she's on her way.
Okay. Sure. Tenure at math.sfsu.edu and graduate, is that what you guys' list is called? Graduate at math.sfsu.edu and lecturers at math.sfsu.edu. And majors. Problem with majors is that I think it's going to bounce when you do that. I always try to email them and it always bounces. Did this start recording? Did you hear it? I feel like it should have started already. I mean the well, actually there is a light that I can see. Oh, no, there's a new camera. I think it started recording and Arik didn't tell us. No, right? Sometimes it's quiet. Okay. Okay, so we've been talking about computing characteristic polynomials using this wonderful finite field method, and today I wanted to discuss another very nice family of arrangements called the Catalan Arrangement. So this is an arrangement that I'm going to denote curly Cn. And it's going to look a little bit like the braid arrangement. So it has all the hyperplanes of the braid arrangement, but it has more hyperplanes. So it also has one with a -1 and one with a 1. Okay? So for every pair I and j, there's 3 hyperplanes at -1, 0, and 1, and they're parallel to each other. So it's like you're taking each plane of the braid arrangement and moving it up 1 and moving it down 1. Okay? So let's try to see what this guy looks like. For example, for C3. So let's draw the braid arrangement first without the -1 and the 1. So you've already seen this one several times. It looks like this, right? Okay. So maybe let me just make sure that I label it just like I did here. So this is going to be x1 minus x2 equals 0. This is going to be x2 minus x3 equals 0. And this one is going to be x1 minus x3 equals 0. Okay? And then, for example, this one right here is going to be the region where x1 is bigger or smaller? Bigger. Okay? So that's the braid arrangement, but then what I need to do is add some hyperplanes by basically shifting each one of these hyperplanes up and down by 1 unit. Okay, so for example, here I've shifted it 1 unit in this direction, and actually it's a little bit hard to draw correctly, but so it looks like this. Okay, so I take each hyperplane and I move it up by 1 and down by 1. And I tried to draw it as well as I could, but for example, here these things should be just 1 point. So it looks something like this. Okay. So that's the Catalan arrangement C3. And this is no longer the region x1 bigger than x2 bigger than x3. Okay. Well, I mean, let's maybe say so when I say x1 bigger than x2 bigger than x3, it's this region of the black hyperplane, but it's going to be split up into a bunch of little red regions. Okay. So that's the arrangement that we're going to consider. And I would like to again do what we've been doing. So compute the characteristic polynomial, compute the number of regions. Here, for example, you see that maybe this is the first interesting example where we have bounded regions, because so far every example the number of bounded regions was 0, but here we actually have bounded regions. Okay. So let's compute the characteristic polynomial. And since the finite field method works so well for us in the case of the braid arrangement, let's try to do it. Let's try to apply it here also. So this is going to be the number of points x1 up to xn in the finite field fq to the n on no hyperplane. In other words, they shouldn't satisfy any of these equalities, right? So such that xi minus xj is never equal to minus 1, 0, or 1. Okay. And now it becomes a purely combinatorial problem. Now, let's do an example. Let's say that n is, I don't know what I made n. Let's say that q is, maybe, let's do this. It's, as you know, it's sometimes useful to think of the finite field as going around a circle so that we go 0, 1, 2, and then it wraps around to 0. Okay, so I'm going to do that. And let me put little circles for the elements of the finite field, and hopefully the number of circles will be prime when I'm done. Help me out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So either 17 or 19. Wow. 13, 14, 15, 16, 17, 18, 19. Q equals 19. And let's say that n is, I don't know, 6. Okay? So this is 0, 1, 2, 3, up to 18. Okay, those are the elements of the finite field. And so what does an element of this set look like? Well, you just have to choose 6 coordinates, 1, 2, 3, 4, 5, and 6. And you just have to make sure that you don't choose any two numbers that are equal or that differ by 1 in either direction. Okay? So, I don't know. I'm going to make you guys do it. So, Tia, give me a number in this finite field between 0 and 18. 7. 2. Give me the next coordinate. 3. Ashley. 5. Jimmy. It's getting harder. 11. Abraham. You need to give me a number between 0 and 18, but it cannot be any of these or a neighbor of any of these. 15. Enrica. Which one? 18. Okay. So that's an example of one of the points that we're counting here. 18 is -1, yeah, but that's fine because it's not a neighbor of any of these things. Because it's not that xi cannot be -1. It's that no difference can be -1. Now let's represent this point by putting dots in this picture. Okay. So actually, let me go around the wheel and just label everything. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. And now let's take these points and put them in here. So for example, 7, this is the first coordinate. Okay, first coordinate. Then 3 is the second coordinate. 5 is the third coordinate. 11 is the fourth coordinate. 15 is the fifth coordinate. And 18 is the sixth coordinate. Okay? So clearly this is a bijection, right? I mean, for any string like this, I can write down the numbers, and the condition that I'm going to have is that these numbers are all labeled differently with the numbers from 1 up to n, and I'm not going to have two neighbor red dots. That's what it means to be off of these hyperplanes. So this is the number of ways of coloring n dots red, numbered 1, 2, up to n, no to adjacent reds. Okay. And so now it's basically just a matter of solving this counting problem. How many ways are there to do that? Okay. And I'm going to solve this problem as follows. I'm going to say, okay, to choose these dots, the first thing I'm going to do is decide which one is dot number 1. Okay. So first, I'm going to choose who gets the label, who gets to be red dot number 1. Okay. So how many possibilities are there for that choice? Well, there could be any dot, right? So there's q possibilities. Okay. Step 2. What I'm going to do, oh man, should change the battery. Okay. Okay, so now once I've chosen my dot number 1, then what I'm going to do is I'm going to take this finite field and unwrap it and just make it into a straight line. Okay. Unwrap the circle, and so it's going to look like this. You should have chosen a smaller cube. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay? So I dropped the first red dot, and then I unwrapped my finite field, and now I'm going to introduce the other dots. On that line. Okay, so you should think that, for example, here, because I chose this position to be 7, then I get to put, here's 8, here's 9, 10, and so on until 5 and 6. Okay. And now I'm going to choose the positions of the other red dots. Now, how many other red dots do I need? Well, I already put one down, so I need n minus 1 of them. Okay? And I have to choose them. Well, so for example, the choice that I made in this case is 11, then 12, 13, 14, 15, 16, 17, 18, 0, 1, 2, 3, 4, 5, and 6. Okay, so I need to choose some of those dots, n minus 1 of them. And what do I need to make sure? I need to make sure that these gaps are at least of length 1, right? Is there anything else that I need to make sure of? You should realize that I'm also not allowed to put a dot right next to the dot number 1. So I also can't choose the number 8. So this gap also needs to be at least 1. And by the same reason, this gap also has to be at least 1. Okay? But now you should realize that choosing the dots is exactly the same thing as choosing how big the gaps are. Okay? So let's say that we chose these numbers A1, A2, A3 up to A, how many? AN. Okay. There's n because there's n gaps in between the n dots, a circle. Okay. So equivalently, I need to just choose what these gaps are. Right? And if I tell you the first gap is 3 long, the second gap is 3 long, the third gap is 2 long, then you know where the red dots are. Okay? Now, what do these gaps have to satisfy? Well, like I said, they need to be at least of size 1, and they need to add up to the correct length. So what's the correct length? A1 plus A2 an should be equal to what? It should be equal to the number of white dots, right? And how many white dots do I need? Well, q minus the red dots. So q minus n. Okay? So I basically need to choose some numbers that add up to q minus n. And they should be non-negative. They should be positive numbers. And if you remember, actually, we already solved this. Because we said there's this very nice trick for doing this, which is to say, oh yeah, well, I'm going to write q minus n as 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus. So there's q minus n things. And I'm going to choose n of the pluses. Sorry, n minus 1 of the pluses. So I choose this plus and this plus and this plus 1, 2, up to n minus 1 of the pluses. And then I'm going to get a way of writing q minus n as 3 plus 4 plus 4 plus 2. Okay? So choosing the AIs is the same thing as choosing which one of these pluses you're going to keep and which ones you're going to ignore. So how many choices are there to do this? Well, if I write q minus n as a sum of ones, I need q minus n minus 1 plus signs. And out of those, I need to choose n minus 1 of them. So this is the number of choices for that second step. Okay. So first step, q choices. And second step, q minus n minus 1, choose n minus 1 choices. Okay? And so where am I now? I have my dots. I know which one is dot number 1. I have all the other dots, but I haven't decided what labels I'm going to put on each one of these dots. I haven't decided which one of these dots is 2, 3, 4, 5, and 6, and I need to do that. And so step 3, decide which are dots, or in other words, label the remaining n minus 1 dots with the numbers 2, 3, up to n. I don't use the number 1 because I already decided which one dot number 1 was going to be, right? How many ways are there of doing this? Well, this is just a permutation of the numbers from 2 up to n, right? In this case, we chose this permutation to be 4, 5, 6. Well, maybe I shouldn't write it here because this is not part of step 2. It's part of step 3, where I take my dots and I decide that the first one is going to be called 5, 4, then 5, then 6, then 2, and then 3. That's just a permutation. And so there's n minus 1 factorial choices. Okay? So that's the number of possibilities for the third step. Okay? So that means that basically I've solved the counting problem. This is just q times q minus n minus 1, choose n minus 1, times n minus 1 factorial. Okay. And let's just simplify this a little bit, because this is q minus n minus 1 factorial divided by q minus 2n factorial times n minus 1 factorial. So here I'm just saying a choose b is a factorial over a minus b factorial, b factorial. Okay. And that's a nice thing to do because now these guys cancel. And so what you're going to get is q times this over this, which also cancels a lot because what is q minus n minus 1 factorial? It's the product of q minus n minus 1, q minus n minus 2, q minus n minus 3, etc. q minus n minus 1, q minus n minus n. You keep going all the way down to 1, right? And what is q minus 2n factorial? It's the same thing except that you start at q minus 2n factorial. Okay. And so what that means is that all of this stuff cancels. And all I'm going to get is, let me just write the answer here, is q times q minus n minus 1 times q minus n minus 2 times q minus n minus 3 up until q minus 2n plus 1. Okay. That's it. So again, that's a very simple formula. It's a very explicit formula, and it's a very beautiful formula because, like I said already a couple of times, if you compute some characteristic polynomial, it's just some polynomial, and there's no reason a priori to think that it should factor so beautifully, but this one does. Factors into this very nice expression. Okay? Okay. Any questions about this computation? By the way, I think I should make a comment that I didn't list combinatorics as a prerequisite for this class, and I have been using it sometimes. And for example, here, this is an argument that if you've taken a combinatorics class, then maybe this is very comfortable. And if you haven't seen this kind of argument, then hopefully you kind of see. It should look plausible to you. But if this doesn't come very naturally to you, then I very much encourage you to take Matt Beck's class in combinatorics next semester. Which I think is a great complement to this one. It's definitely not replaced by this one, and I think it'll be a very good class. Okay. So once we have the characteristic polynomial, we should figure out how many regions this thing has. Okay. So let's do that. And we know that that's easy now. So what is the number of regions of this arrangement? Well, we just need to plug in minus 1 and take the absolute value by Soslavsky's theorem. So let's do that. Okay. So I plug in q equals minus 1. So here I'm going to get, just like we keep doing, I'm going to get a minus 1, and I'm always going to ignore the minus sign. So minus 1, I don't even look at it. Then minus 1 minus n minus 1, that's going to be minus n plus 2. So I get n plus 2. Then minus 1 minus n minus 2 is minus n plus 3. So I get n plus 3. And so on, n plus 2, n plus 3, n plus 4, until minus 1 minus 2n plus 1 is minus 2n. And so I get 2n. Okay? So that's it. It's a very simple formula for the number of regions. And I can write it a little bit differently if I prefer. I could write it as 2n factorial. So that's the product of the numbers from 1 up to 2n. And then divide by n plus 1 factorial, which is what I don't want here. Okay. So that's the number of regions. It's very simple. Does that look familiar to you guys? Maybe. Maybe not. There's one thing that I would like to remark here, which is that you can see that this is a very symmetric arrangement. You can see the symmetry. Okay? And I kind of highlighted this special region. Of the braid arrangement. Okay? And inside there I have some sub-arrangement and I have some regions. Okay? But you see I have 6 of these regions and they all look the same. And that's a symmetry that I have because here if you flip I and j you're not changing anything. If you relabel the coordinates you're not changing anything. Okay? And so that means that no matter what reordering of the coordinates you have, you're going to have the same arrangement. And that means that in each one of these chambers, you're going to have the same picture. In this case, there's 6 chambers. In general, there's n factorial chambers. Right? So let me say that the arrangement Cn looks the same inside any of the n factorial regions of the braid arrangement. Okay. In particular, that must mean that the number of regions is a multiple of n factorial. Right? It's n factorial times however many regions you have inside each little wedge. So let's figure out how many regions are there in each wedge. Number of regions of Cn inside each wedge. And by a wedge I mean a region of the braid arrangement. Well, it's basically the total number of regions divided by n factorial. So that's 2n factorial divided by n plus 1 factorial times n factorial. Okay. Does that look familiar now? I see a couple of nods. I can write this a little bit differently. If instead of writing n plus 1 factorial, I write it as n plus 1 times n factorial. Right? N plus 1 factorial is n plus 1 times n factorial. And then I keep the other n factorial. And then you see 2n factorial divided by n factorial is 2n choose n over n plus 1. Okay. And maybe I can see a couple more nods now. Maybe that looks familiar. These are exactly the Catalan numbers that we've discussed. These numbers are the answer to everything. We saw that they are the numbers of triangulations they're the number of triangulations of a polygon, and we saw that they're the number of these little staircases that we called dig paths. And they're the answer to this question also. The number of regions of the Catalan arrangement inside each wedge is the Catalan number. And, well, maybe you should have expected it all along because I called this the Catalan arrangement. Okay? I don't know how surprising this is at this point. But anyway, so that's where it gets its name. And when you have a result that nice, you want a better explanation. I mean, okay, this is a proof, but we had to cancel a bunch of things, compute in a finite field. Okay, that was fun, but that doesn't seem like it should be the explanation that really tells us why that's the number of regions. Okay, so let me show you a better explanation for this fact. Let's just focus on one of these wedges. Well, maybe let's do another computation first. So I'm going to erase this. This is 2n factorial over n plus 1 factorial. So I'll erase this. And I can write this as n factorial times c sub n. Okay, so like we said, this is the number of wedges, and this is the number of regions per wedge. Okay. But maybe before we try to really explain that one, let's also compute the number of bounded regions, because that's, like we said, this is the first time that that's an interesting number. Because so far that key is being 0 because we keep looking at central arrangements, but this arrangement is not central. Not all the hyperplanes go through the origin, so we actually get some bounded regions. Okay. So Saslavsky's theorem tells us that all we have to do is plug in 1 and take the absolute value. Okay. So let's see what happens when we do that. So q is 1. So here we just get 1. Then 1 minus n minus 1 is minus n. And I ignore the sign, so I get n. 1 minus n minus 2 is minus n plus 1. So n plus 1, n plus 2, dot, dot, dot. Here, q is 1, so 1 minus 2n plus 1 is minus 2n minus 2. So it goes to 2n minus 2. Okay? And this is 2n minus 2 factorial divided by n minus 1 factorial. Okay? So again, that's a simple formula. Let's write it out. 2n minus 2 factorial over n minus 1 factorial. Okay. And now let's compute the number of bounded regions in each wedge. So I'll insert the adjective bounded here, and then I'm going to divide this number, 2n minus 2 factorial over n minus 1 factorial. That's the number of regions. And now I divide by the number of wedges to get the regions per wedge. Okay. So I get this. And again, let me take this n and write it as n times n minus 1 factorial. N minus 1 factorial times n minus 1 factorial, and 2n minus 2 factorial. And this thing is 2n minus 2 choose n minus 1 divided by n. Okay. So you saw that the previous answer was 2n choose n divided by n plus 1. And now it's the same thing, except that instead of n, I have n minus 1. This is precisely the Catalan number, but the previous one, the previous Catalan number. Okay. So again, that's a very pretty answer, and that must mean that there's something here we're not understanding. Because that's too nice to have to go through such a long computation. It's not a long computation, actually. It's not too hard, but I think it begs for a better explanation. So let's do that then. Let's let's try to really understand why this is. So let's look at this wedge, where x1 is bigger than x2 is bigger than x3. Okay? So this is x1 equals, let me write it the way that I wrote it there. So this x1 minus x2 equals 0, and this is x2 minus x3 equals 0. Okay? And then, for example, let's look at the hyperplanes x1 minus x2 equals minus 1 and x1 minus x2 equals 1. Okay? So you notice one of them is outside the region and one of them crosses the region. Okay? If x1 minus x2 is minus 1, that means that x1 is less than x2. Right? And so that means that you're not in this region. In this region, x1 is bigger than x2. On this hyperplane, your x1 is less than x2. So that means that this hyperplane doesn't interact with the region that we're interested in. Only this one does. And by the exact same argument, only x2 minus x3 equals 1 touches our main region and the other one doesn't. And for the same reason, x1 minus x3 equals 1 touches it and the other one doesn't. Okay. So that means that this is going to look like this. Well, like this, and this. Okay. x1 minus x2 equals 1. x2 minus x3 equals 1. And x1 minus x3 equals 1. Okay. And I want to argue that the number of regions, which in this case is 5, is precisely the Catalan number. Okay. So what I'm going to do is that I'm going to give a combinatorial label to each region in the following way. Label I mean, how do you specify a region inside this black wedge? All you have to do is, for each purple hyperplane, you have to tell me, am I on the positive side or am I on the negative side? Okay. And so what I'm going to do is basically, for each region, I'm going to make a list of the hyperplanes for which I am on the negative side. So label each region with the pairs ij for which xi minus xj is less than 1 in that region. Okay. So here x1 minus x3 is less than 1, here x2 minus x3 is less than 1, and here x1 minus x2 is less than 1. And so then I say, for example, this one. So look, you look at this one, and it is on the negative side of 1, 3, of 2, 3, and of 1, 2, of all three of them. So I write all of them, 1, 2, 1, 3, and 2, 3. Okay? Now here, I crossed 1, 3. So now I'm no longer on the positive side of 1, 3, only on the positive sides of 1, 2, and 2, 3. Okay? Now let's go over here. Here I'm crossing the hyperplane 1, 2. So now I'm only on the negative side of 2, 3. But I'm on the positive side of 1, 2, and on the positive side of 1, 3. I cross 2, 3. And now I'm only on the negative side of 1, 2. And I'm on the positive side of 2, 3, and of 1, 3. And finally here, I am on the positive side of all three hyperplanes. Okay? So, nothing. Okay? Now, there's something that you should notice about this. If xi minus xj is less than 1, right? In other words, if ij is in the label, then I can also say that xi plus 1 minus xj is less than 1. Why is that? You should think that the numbers are, oh, I think I chose the other region. Give me just a second. So remember, the inside this region, the x's are sorted in decreasing order, right? So I'm saying if xi minus xj is less than 1, I don't know, let's do it with a concrete case. So I'm saying, if x2 minus x5 is less than 1, then x3 minus x5 also has to be less than 1 because 3 is closer to 5. If the distance between here and here is less than 1, then by moving to here, the distance is even smaller. Okay? And also, if I move this number to the left, that's also going to be smaller. So xi minus xj minus 1 is less than 1. Okay, so I have these two properties. Okay. So what I'm going to do now is a little bit different. Instead of making this whole list, I'm going to just make a bunch of little dots. Okay? So instead, I'm going to put a dot on ij. So for each region, I'm going to make a diagram of dots where the dot with a dot at ij whenever ij is in the region. Okay? So let's do first a small example and then we'll do a bigger example. Okay? So here I'm saying I have 1, 2, 1, 3, and 2, 3. So I'm going to just make dots at 1, 2, 1, 3, and 2, 3. Okay? And this diagram is going to represent this region. Okay? So I just encode these into dots so I can have a nice little picture to work with. Okay? Now, according to this picture, what am I saying here? What is this rule saying? I'm saying that if you have a dot at ij, then you better have a dot at I plus 1j. So this dot is forced. And you better have a dot at ij minus 1. So this dot is forced. Okay? So basically I get to put dots, but they have to satisfy these properties that they're kind of going, they're close and they're going right and going down. Okay? So that's a small example and it's too small to know what's going on. But let's do a bigger example. With n equals 6. Okay? So here my board is going to be bigger. Okay? And I need to put some dots. Now one thing you'll realize is that I always put dots when I is less than j, right? The dots are always above the diagonal because always the first label is smaller than the second label. So that means that there's not going to be any dots over there. The dots are above that diagonal. Okay? And also, this is where I is 0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I also don't have any dots here, right? Because I cannot be 0. So there's no dots here. Okay? There's no dots here. And what's the largest dot that I could put? I mean, basically, the places where I can put dots are these ones, right? Those are all the possible pairs of I less than j. Okay? And so to record the name of a region, I just have to put dots in this picture. But I have to be careful to satisfy this condition. Okay. Again, I'm running out of battery. Give me a second. We'll see. Okay, so let's try to put some dots in this picture. So let me pick on somebody that I haven't picked on. So Nick, what dot would you like to put on this picture? Just choose one. So we can put 5, 6, for example. 5, 6. Okay. Tristram. 2, 5. Okay. So Tristram wants to put a dot in 2, 5. But then you realize that if I want to put a dot there, then I better put a dot here and here.